Hello, everyone. After a bit of hiatus, I'd like to welcome everyone back to the IOP lectures held at the Open University. I hope all of you joining us are well. I'm afraid that we're still online for now, as the approach towards COVID at the OU is still very cautious, but more OU business is being conducted on site, so we're hopeful that in the near future we might be able to host some of you in the Beryl Lecture Theatre and provide a stream online for those of you who have joined for the online sessions that we've been holding in the meantime. I'll start, as per usual, with a few bits of housekeeping. So I'd like to take this opportunity to advertise an Open University inaugural professorial lecture next month, which occupies our normal second Tuesday of the month slot. So that will be on the 10th of May. And Professor Leslie Budd will be giving a talk entitled From Urbanite to Astronaut, the Territorial Economics of Space. This promises to outline some of the socio-economical impact of space exploration beyond just the scientific outputs. If you want to join that talk, if you just Google Leslie Budd inaugural lecture, then the first couple of results on Google come up with a link where you can register to either attend in person or online. Beyond this, we plan to continue with our IOP lectures going forward, but our future lineup is still to be confirmed. Those of you who are already subscribed to our mailing list, please keep an eye out for reminders or any changes to this. And to keep up to date, please either email us at stem-sps-admin@open.ac.uk or through the IOP email marketing list, which is emailmarketing@iop.org. And if you ask through those emails to be added to the Milton Keynes Talks email list, then you'll be made aware of any future upcoming talks. You can also follow us on social media. I should probably say our previous stream talks are all available on the Open University School of Physical Sciences YouTube channel, if you have a Google for that. This lecture will also be recorded and uploaded to the YouTube channel at a later date, or if you just rejoin the link that you're joining today on Stadium, the recording will be up in the next few days and you'll be able to rewatch it from this same link. As per usual, if you want to ask any questions to the speaker, that will be done through myself. And in order to ask a question, if you can email any questions to stem-sps-iop-lecture@open.ac.uk, the link should be on the webpage that you're watching us from at the moment, and questions will be asked to Kasia at the end. Now, on to the main event. It gives me great pleasure to welcome, I'm going to try this once, Krzyzanowska, who from here on out I'll refer to just as Kasia, to just welcome her for joining us today. She earned her PhD from the Open University, where she worked on an experimental cold atoms platform for quantum computing alongside Silvia Bergamini in her research group. And since 2018, she's worked at the Los Alamos National Laboratory as a staff scientist. She leads 2 projects and participates in numerous collaborative proposals developed across the Los Alamos National Laboratory. Her current research focuses on ultra-cold atom systems, and in particular, using Bose-Einstein condensate. What I've got written here has got an error in it, Kasia. Bose-Einstein condensate guidance in optical potentials for quantum sensing. Does that make sense?
Yes, sure. Sorry, I'm got distracted with coming in emails. You know, technical issues always must be the first thing that happens during the talk.
Just close everything.
Yes.
So thank you so much, Kasia. So, and you'll be giving us a talk today entitled Atom Gyroscopes, Exploiting Quantumness of Cold Atoms for Sensing. So please, if you'd like to share and take it away.
Okay, well, thank you, Ben, for such a lovely introduction. And thank you, organizers, for having me here today. I am going to talk about atom gyroscopes exploiting quantumness of cold atoms for sensing, mostly. And so I'll start with an introduction, an overview of quantum technologies to give you an idea, the context for the research that I work on. And I will also introduce the LAM team. It's a quantum technologies team that focuses on cold atoms for quantum technologies. Then I will dive in some more technical details. I will talk about rotation sensing using atoms, then about how do we use guided atom interferometer to perform rotation sensing. I would like to mention a little bit another angle of our research where we try to go beyond standard quantum limit. Standard quantum limit is a typical limitation that any kind of classical devices currently is subject to. And finally, I will talk a little bit about Quantum Enigma, a board game, which is an outreach tool that I developed together with the Open University, working with Silvia Bergamini and Andrew Norton. Starting with the introduction, what are quantum technologies? Quantum technology is an emerging field, so I'm going to read this definition here, an emerging field of physics and engineering, exploiting the principles of quantum mechanics, such as entanglement and quantum superposition, to design new class of devices with enhanced performance. So it's an emerging field, meaning that it's kind of a difficult thing right now to classify systematically all the efforts which are going on in this field. But here I listed a couple of applications, typical applications that you can come across of quantum technology. So the first one is quantum computing, and I'm pretty sure you've heard about it before. The aim of quantum computing is to design devices, computing devices, that would be able to tackle computational problems which are beyond capabilities of our modern computers. That is going to include certain optimization problems or number factorization. Another branch, another application is quantum metrology and sensing. The aim of this branch is to design devices that are going to be more sensitive, than classical sensors, to measure magnetic fields, to measure acceleration or rotation, and so on. Another known field is quantum key distribution to provide secure encryption protocols. And finally, less known, typically quantum simulation. This branch focuses on developing devices which are quantum in nature and can be used to emulate some other quantum phenomenon that is difficult to be investigated otherwise. So, for instance, we are interested in some features of solid materials, but we cannot measure them directly, or we cannot figure out how they work directly. So what we can create, for instance, is a lattice of cold atoms that has a similar feature, and then emulate this more difficult physics using quantum simulation. At Los Alamos, you can find pretty much experts in any of those categories. What I'm going to talk about today is mostly quantum metrology and sensing, because this is what we focus on. This is what I focus on. And so this is the quantum technologies team using cold atoms at the Los Alamos National Laboratory. We have 3 staff scientists. It's me among all of them. We have 7 postdocs currently. And we also have students every summer. It's not summer yet, so I don't have a big list of students, but we will have probably more this summer. So Los Alamos is placed in New Mexico in the US. And this picture here shows the actual laboratory and the Los Alamos town. So as you can see, we are at the edge of a mountain range. And the lab and the town is placed on a couple of mesas. In fact, if you have this image, Los Alamos is a desert and flat and low. This is actually not this kind of desert. It's a high desert, high altitude desert, meaning that we mostly just live in mountains. It's a pretty pleasant place to live. So what do we do in our group? I have selected just a few projects to show you what is the spectrum of work of work that we are working on. But I'm going to focus later on two of them, which are those two. So for instance, we can use machine learning for quantum technologies. We have a project that my colleague right now is leading to improve speed, quality, and robustness of the experiments. We are trying to use machine learning to design exotic or like maximally entangled states for quantum sensing and so on. Mike also is working on emulating quantum magnetism with regular atoms. So this is from the quantum simulation side, where we create a well-defined, reconfigurable system, and we use it to study something which would be otherwise very difficult to be studied, such as quantum magnetism. And then two other projects I'm going to talk about, and I worked a good amount of time over the last 3 years, is the first one, guided atom interferometer for rotation sensing. So this is what the topic of this talk is about. And the aim of that is to demonstrate experimental implementation of rotation sensing using neutral atoms, as well as maximize sensitivity of the device, because it's not enough to just show the proof of principle is doable and how to do it. We also aim at improving the performance of the device and potentially making it applicable and, maybe not on the market from our side, but make it available for other people to bring it to the market. Another project I will mention at the very end is algorithms and implementations for robust quantum metrology and sensing. And this is kind of a step up from the previous project from guided atom interferometer. So in quantum technologies, we distinguish something as quantum revolution 1.0 and quantum revolution 2.0. So 1.0 is everything that has been happening for the last 30 years up until a few years ago, when we're mostly using some feature of quantum mechanics, such as superposition, to get quantum advantage over classical devices. But now we are going to focus on creating more exotic quantum states, which are having quantum correlations in them. This is something I'm going to touch on later on, which are going to increase sensitivity even beyond what we have nowadays. To give you an idea of what sort of experiments we are talking about, since we are cold atoms for quantum technologies, everything that we do uses cold atoms. So even though the experiments differ slightly, they all look to some degree similar. So here is the picture of one of the labs. It's a rubidium lab, and it's actually the atom rotation sensor. All of that, what you see over here, is a single experiment, in fact. So we have two optical tables and a control system. So as you can see, typically those kind of experiments, they have a whole bunch of optical components and lasers. And the reason for that is because we use lasers and optics to prepare laser light that can interact with atoms in a certain way. So we can trap them, we can cool them, we can manipulate their state. That's why here to the left, the entire table is just laser table. And here to the right, you can see mostly optics. And then there is a vacuum chamber buried somewhere all among these optics. It's, comparing to the optics, it's pretty small part of the setup, where we have atoms in vacuum chamber because we want atoms typically to be isolated from the environment so that the environment does not messes up with our, does not interfere with our quantum states. And typically you can also see all of that sits on a huge optical tables, which are very heavy and supported by special legs that isolate vibrations from the ground, because the experiments are very sensitive to any kind of external noises. We also need a system to control the entire experiment and to measure what's happening with the atoms inside. And so this is like our main workstation. We can sit behind this computer and set up the experiment and measure the outcome. Okay, let's move now to rotation sensor using atoms. I would like to introduce you to this idea before I actually talk about the particular implementation of the project. So first of all, why is rotation sensor important? Why is it important for us, for everyone else? And the answer to that is because we would like to improve inertial navigation systems. So what are the inertial navigation systems? If, in case you don't have a GPS and you want to move around, you could use a navigation system, inertial navigation system, which is a self-contained navigation technique. The premise of it is that if you know your starting point, and you can look now at this picture to the bottom left, if you know your starting point and you are, for instance, on a plane, and the plane you are traveling on has 3 accelerometers and 3 gyroscopes, so it can measure the accelerations of the airplane and also the orientation and the rotation of the airplane, you could estimate, you can measure where you are at a certain time after you left the starting point of your journey. And that sounds easy, but in reality, it's not that simple in practice. And the reason why it's not that simple in practice is because, unfortunately, the inertial navigation system is not very accurate. So here to the right, I have a graph that shows you that if one was to use the inertial navigation system only, so the 3 accelerometers and 3 gyroscopes, the error in position, so like you start in one city and you want to go to another city, the error in position grows with time roughly exponentially. So within the first half an hour, you are pretty sure where you are, but after 3 or 4 hours, you are away from the destination point that you were trying to travel to by hundreds of kilometers. And that's a pretty big distance. That means that if you start your flight in Eastern Europe and you want to go to the West, within 2-3 hours of flight, you would miss the airport completely. So here to the bottom left, again, I show one of the approaches to measurement of the rotation, which is a mechanical gyroscope. They been the first devices used for inertial navigation to some degree, but they are not accurate nowadays to use them. In fact, what we use is rotation sensors that use interference. And now I just want to say, bear with me, this is probably a little bit more complex slide, but I'm going to explain to you what interference is and how can we use it to measure the rotation. So let's look first at the bottom left scheme, the picture. Here I show the configuration known as Michelson interferometer. So we have a light source, laser, typically, and then the laser beam is being split on a semi-transparent mirror into 2 arms, 2 interferometric arms. This is how we call them. So one beam travels, is reflected by a fully reflected mirror, comes back, the same with the other arm. Both of the beams are combined again on the semi-reflected mirror and reflected to the detector. The question is, what are we going to see on the detector? So it turns out that depending, if we start adjusting the length of one of those, so let's keep one of the arms constant length and the other we start adjusting the length, what we are going to see on the detector is either maximum light, or we can either see no light at all. And this is presented here in this little graph. It looks like this kind of cosine. We can also see some light in between, depending on how we adjust the length. Why is such? Well, the light has a wave-like nature, meaning that as it propagates in the arm, it can be expressed as it is shown here on those 2 pictures as a wave. So let's say the red one is one arm and the yellow one is the other arm. if both of the waves in both arms, the moment they come and recombine on the half-silver mirror, if they are in sync, so as it is shown here, the valleys are in the same places and the tops are in the same places, then at the output, these waves add up, and what we have is a constructive interference. This is how we call it. So we see maximum of the light on the detector. If, on the other hand, the second wave is shifted in respect to the first wave, and in this case, if it's shifted by the entire, by 180 degrees, then the combined wave at the end, it's just nothing. So we are going to see nothing on the detector. That's why what we are going to see is something known as interference fringe here. This is the one I'm showing, which shows the light intensity on the detector depending on the relative length difference of the arms. Well, that is what the interferometer is, generally speaking. But how can we use it now for the rotation? So if you now look to the right, this is the interferometer application for rotation. You can see that the implementation has been changed a little bit. So instead of having just one arm which is being transmitted and reflected back to the detector, we now create a loop. We allow the light in one arm to travel one direction, so basically right, top, left, and down, while the other arm is traveling the opposite direction. Well, in this case, what we expect to see on the detector is maximum light because the arms, one loop direction and the other loop direction have the same length. There is, however, a very subtle feature effect is that if we start rotating that system, the system that I'm showing over here, let's say to the right, what we are going to do, we are going to effectively shorten a path traveled by light in one direction and expand the path traveled by beam the other direction. As a result, is the same as tuning the distance of the relative length of the arms. And we introduce a phase shift, which in this case is proportional to the area of this enclosed loop and how fast we are rotating the entire interferometer. So what we are going to see at the output is, again, this kind of interferometer fringe, but this time the how much light we see is going to depend on the induced phase shift. So basically, the rotation multiplied by the area that we enclosed in the arms. Point out. So that is the most important takeaway from now, because I'm going to show you later on plenty of data, the data that we took in the laboratory, and all of that literally just looks like this picture. I mean, they are all just cosines, which are bigger, smaller, more to the right, more to the left. This is what science is about. You measure the same time over and over again, and you try to understand what impacts it. But the point is, just remember this picture. This is what I'm going to show later on again. Well, so far I talked about interferometer with light. And this is something pretty natural for us because we are accustomed to laser light, even with laser pointers. So we know that they have that they can diffract, they can interfere with each other. It's pretty intuitive, I would say, nowadays with our technology. However, the question is, how do we do this with atoms? I mean, do atoms behave like light? Well, it turns out that atoms, just like photons, can also create interference patterns. And the reason for that is that every object has associated with it a de Broglie wavelength, which is a quantum mechanical property. It's something we don't experience on everyday basis because objects are so big that we just don't see the wave nature of the big objects. But on the small scale, on the atomic scale, atoms have this de Broglie wavelength, so they also can behave wave-like under certain circumstances. And so, interestingly, the sensitivity of the rotation sensor depends on the energy carried by the particles. I did recall again here that scheme showing the Sagnac interferometer and what the phase shift depends on. So it's not only rotation and the area, but it's also the energy carried by each particle. So in case of photons, I mean, they carry a certain amount of energy, which is defined here as h bar omega. So this is the frequency of each photon multiplied by Planck constant. In case of atom, the amount of energy that atom is going to carry if we somehow split it and move it in the loop is equal mc squared. This is the famous equation. If we compare the energy of atoms and energy carried by photons, we can see that energy carried by atoms is orders of magnitudes higher than the energy carried by photons. It's 10 to 10th. So we can estimate that this shows us that atom interferometers promises a significant sensitivity improvement in this case, if we can, enclose the same area. And now I would like to just tell you that this kind of experiments have already been shown and done, and it's possible to make atom interferometers, and there are already devices that show the full potential of atom interferometry, and they are called Freespace atom interferometers. So the premise here is that you start with a beam of atoms, it's like a jet of atoms, and then you expose it to a couple of laser light beams which split atoms in the beam into two paths and then recombine, just the same as if we were doing it with the laser light. Then at the end, you can measure how many atoms end up in one arm and how many atoms end up in the other arm. And this way, you can figure out what was the relative length of those arms. So whether you see majority of the atoms in one output or in the other output. And this kind of interferometry has been already demonstrated and even benchmarked in difficult situations such as at the airplane, when the conditions are very tough. You have lots of vibrations and lots of movement of the entire experiment. So it's very impressive. However, there are two problems to this kind of implementation. The first one is the platform of motion. Because atoms are propagating free space, it's a jet of atoms that just goes through the space. If the entire experiment suddenly is going to be moved very fast, the atoms which are propagating are just going to smash against the wall of a vacuum chamber, and you're not going to see any, you're not going to detect any signal. Other problem with this kind of approach is the size. In order to have high sensitivity of this kind of interferometer, you need to allow those atoms to propagate on a long distance, meaning that those devices at least need to have a length of a meter or so on. I mean, this is not a pocket-sized device. And the solution for those two problems is, well, let's still use atoms, but let's maybe guide them. Let's maybe confine them in some kind of guiding potentials, which are going to ensure that, one, we don't smash the atoms against the wall when we move the experiment too fast, and two, we can somehow guide them along so that the area is big, but the science package, the experiment, is not big itself. So after that introduction, now we can finally move to our guided atom interferometer. So this is precisely what we do. These are the pictures I have already shown you. This is the experimental setup. It's pretty complex, to be fair. There are many cooling stages, but I think it can all be summarized in this. Those two pictures can be all summarized in this very simple scheme, which shows a simplified experiment. It shows that vacuum system is needed, first of all, to keep atoms isolated from the environment. So this is the vacuum system. It's obviously way bigger and complex in reality, but let's assume that's it. Then we need laser cooling and trapping techniques to prepare atoms. So to trap them, to cool them, to manipulate their internal states. So this is represented by those laser beams which are crossing here. And finally, we need imaging system to take measurements. So I'm going to show you pictures of the atoms. Later on, every single time we want to take a measurement, in our case, we literally just take a snapshot of atoms there and we just measure the populations and what they are doing. That's what we do. However, two key techniques that I would like to mention here that we use. The first one is Bose-Einstein condensate. This is an exotic, it's a certain kind of state of matter. It's something that we definitely don't encounter on a daily basis. So in this state of matter, particles of gas are cooled down to temperatures close to absolute zero. And I'm talking here about, nanokelvins, tens of nanokelvins, maybe hundreds of nanokelvins. Once you do it, all particles start occupying the lowest quantum state of the trap that they were prepared in, and they form an entity described by a macroscopic wave function. It sounds complicated, but what I'm trying to convey here is that when you cool atoms so low, they kind of condense together, and instead of behaving like individual atoms, they start behaving like a wave. So essentially like a laser light, which is very useful for us because even though we could use just single atoms for atom interferometry, as I showed you before, it's doable. This particular state of matter has certain advantages for us that we exploit in our atom interferometer. And the second technique I would like to mention is dipole trapping here. So dipole trapping is a laser trapping technique. And we use, in our case, a single focus laser beam. So it's shown here to the left. So the laser light interacts with an atom which is inside of the beam. The beam induces a dipole moment, and then because of the dipole moment, the atom is attracted to the middle of the potential. So it's attracted to the highest, to areas of high light intensity. So here on the bottom, I just wanted to show you very briefly how we are preparing BC and dipole traps. So we first overlap the beam with a bigger reservoir of atoms. And then when the atoms are inside, this is a thermal crowd. So this is not a BC yet. We just have many individual atoms in the single laser beam. And as we are holding those atoms in a laser beam and making sure that the atoms get cooler and cooler, eventually what we can see is that the atoms collapse to this little point over here. This is a cloud of atoms in BC, which has about 5,000 to 6,000 atoms. Interesting thing is that this is very dense and it's going to behave like a wave in our case. And let's move to experimental protocol. This is also kind of difficult slide, so I will take it slow over here. So picture number A shows the experimental protocol where we prepare the atoms in the BEC in the dipole trap. So I just mentioned the dipole trap. It's actually two dipole traps crossed with each other. This dipole trap beam can be moved to the side up and down because we have another optical element that allows to change an angle at which the light that goes through propagates. So this beam can be moved up and down. And now the protocol goes like this. Here on the picture B, we start with the atoms with a single beam. We use a laser light, which is this yellow beam over here, represented, to split the atoms into two clouds, and those two clouds are propagating in opposite directions along the waveguide. The reason they can do it is because we in fact use BEC, so because it behaves like a wave, it can behave in a wave-like manner outside. Then at some point, we use another pulse to reflect the clouds back towards each other. As they go through each other, so here's the time flow I'm showing you, as they go through each other, they go to the opposite sides, we reflect them again, and when they overlap, finally, what we do, we have another laser pulse which works like a recombination laser pulse. We allow the cloud to evolve, and we take a picture. So the picture we take looks like this here, this C. we see atoms in three peaks, in the middle peak and in the outside peak. And the ratio between atoms in the middle peak to the outside peak is going to tell us what is the is going to show us the interferometer fringe, which looks like this. Just to remind you, I have already talked about interferometer fringe before when we were adjusting the length of the arms. You could see everything in one, everything to the detector going and nothing going to the detector. And the same is over here. You can see all the atoms in the middle, or sometimes you see no atoms in the middle at all, and everything is in the side. So this way we can recover the interferometric fringe. That's the protocol of the experiment. While the atoms are moving out and back, what we do on top, we also move this beam outwards and back, and this way we enclose a area, meaning that if the entire interferometer now rotates, we should see the rotation impact this interferometric fringe. So the results, showing that we are able to see interferometer is not enough, because what is now important is to make this device as robust and as sensitive as possible so that it's usable, that is better than the other kind of rotation sensors. So what we've been doing for the last 3 years is mostly examining sources of noises and limitations, working towards increased performance of the device. And that includes, first of all, testing the performance for various times of the interferometer sequence. So how long we wait before we reflect the atoms and recombine. This is something that's going to indicate how sensitive the interferometer is. But the longer we wait, the more problems we have. So here to the right, I show typically what we do. We take the same fringe, but for different kind of time.
Sorry, everyone online. Just give us a second. Ah, there was a sound. You're here.
Okay, yeah.
Perfect. Yeah, so I think just to summarize, we mainly do two types of tests on our device to benchmark it. One is take the same over and over interference fringes for different times between the pulses and check how it affects the performance of the interferometer. And the other one is Allen deviation, so we check how much our device drifts over time. So we just take the same measurement over again, and we average it down, and we check whether we are still getting a better results or whether at this point it started drifting out and we are just not gaining any additional accuracy. So there are the two main types of experiments we are doing. So for instance, some of the results show that for shorter interrogation times, we do have some noise, but this noise is comparably smaller than for the longer interrogation time. So for instance, for time 80 milliseconds, we have way more noise over here than for time 20 milliseconds. So these are the kind of systematic type of noise sources that we are chasing down in the experiment for the past 3 years. It's a tedious work, I can say. So for instance, we solved one of the issues. One of the, we know that the main source of the phase noise, or one of the noises that we have, is the position of one of the mirror. So here to the top right, I recall the experiment again, and you can see there is a mirror which we use to create this beam that splits and reflects the atom and recombines them. The problem is that this mirror is like a reference point for these atoms. It's like the length of the interferometric arm. So if this mirror starts moving back and forth without our knowledge, we start seeing a noise. And the longer we measure the interferometric fringe, like here for 120 milliseconds, eventually we don't see any fringe at all. Well, fortunately, there are ways to deal with this. We just bought an accelerometer, a very good accelerometer for a few thousand, that cost typically a few thousand dollars at least. And this kind of accelerometer is sensitive enough to measure the movement of this entire experiment. So even though we have experiment on these heavy tables and the legs that insulate the vibrations from the ground, you still can see the vibrations of the mirror that come from the fact that the entire table is still shaking a little bit. So using this accelerometer, we can correct for the space, for the noise, and recover our interferometric fringe the same way, increasing the sensitivity of the device. Another type of experiments we do, again, we take many of those interferometric fringes. As you can see, they all might look the same for you, but for us, it has a very important information in it. And for instance, we can send atoms many times through the same loop and see how that affects the performance of the experiment. And we actually do many more things. I just don't want to make you bored by just watching the same cosine over and over again for a couple of next slides. That is basically what we do in this experiment. It can take a long hours to take those measurements and long hours to analyze and understand. And every single time we find something new, we improve it, we get better performance. We are still not at the final limitation of this this device. I think we can go further with the sensitivity. Okay, so having said that, let's move to quantum sensors 2.0. I was talking about interferometers, and quantum interferometers are considered to be quantum sensing 1.0. And it's because typically atom interferometers exploit the wave nature of ultra-cold atoms for measuring acceleration, rotation, gravity, electromagnetic fields. Well, in our case, rotation. And as I mentioned before, this performance, the performance of interferometers especially, but performance of any kind of classical approach is limited by standard quantum limit, which scales as 1 over square root of n. That means n is number of either particles or repetitions. That means, for instance, if you want to take a picture and the picture is very noisy, you can take many pictures of the same item, average them, and this way you're going to get a better, more clear picture. So if you want the noise to go down by 7 times, for instance, so this delta is phi here, 7 times, then you need 45 repetitions of the same picture to average down. However, if we can engineer some kind of quantum states that have quantum correlations, we can enable phase measurement below the standard quantum limit, reaching something known the Heisenberg limit. So it's a next limitation for this kind of devices, which scales as 1 over n for fully entangled states. You might have heard about entanglement. So this is basically a maximum limit. That means that if you want, let's say, if you have a quantum camera and you want to take a picture and you want to decrease the noise by 7 times, then you only need 7 pictures instead of 49, as if it was in the case of a standard camera. So here to the right, I show, it's kind of a comprehensive picture showing all of the proposals, experiments, and approaches towards quantum sensors 2.0, so quantum sensors which are better than standard quantum limit. And they are trying to reach this orange border over here to the left, known as Heisenberg limit. So that nothing is going to be on this orange side, everything is going to be on this brown side, and the closer to the orange side, the better. So the problem here is that if you look, the stars over here, stars are the only actual experimental implementations. All of the circles are the proposal. So when people said, well, it would be nice to do it, and we expect this and this kind of better performance, but it hasn't been actually shown yet. The reason why it hasn't been shown yet is because engineering quantum systems like that and keeping them isolated enough from the environment so that they stay quantum is really challenging. And you can see that the only experiments that were close enough to Heisenberg limit are the ones which had pretty small number of particles, like 10 particles. it's not a spectacular advantage. Like, at least those experiments here is a proof of principle, but they're not going to be more powerful than a standard atom interferometry, where you have thousands of particles. So the quantum metrology is still far from realizing its full potential. And actually LIGO, so you've heard about LIGO that detected the gravitational waves, is probably the only use of quantum sensing 2.0, which is based on squeezed light, up to date, that uses quantum metrology to beat classical metrology. That means that in this regards, we have still a lot to improve. And that is our second project that we work on, which are algorithms and implementation for robust quantum metrology and sensing. This project is pretty big. It has many threads as both a theoretical effort and experimental effort. The idea here is that you can think of a novel quantum states or novel approaches that are going to be useful for quantum sensing, at the same time to be robust against all of the noise or anything that environment makes the quantum to be hard. So for instance, there is something known continuous variable quantum compiling. Quantum compiling is a kind of like a subroutine used to create optimal quantum protocols and study dynamics of some other experimental systems. It can be very useful. There's quantum machine learning. Quantum machine learning is similar to machine learning, but it's vastly different because it works on quantum states and it evaluates the quantum wave functions to learn using that in kind of a loop. There is some classical element to it, but it's not the core of quantum machine learning. And there's also an experimental effort when we try to create system that will be able to make non-classical correlations between like a single atom and the BC, and show that that can be also used for practical and more robust quantum sensing. I'm not going to delve on it too much because it's a very complex topic. You're welcome to ask some questions if you want. I would like to finalize the talk talking about the game, Quantum Enigma, the board game. So coming back to my very first slide, where I talked about various aspects of quantum technologies and their applications, you can see that, in fact, I only covered quantum metrology and sensing, and in reality, I also just covered a very small portion of it. And it took me a long time to go through the entire presentation and explain step by step how it works. So we thought that it would be great to have a tool which will cover a broad spectrum of research in quantum technologies in a very detailed way, but also show it in a memorable way. We came up with the idea of the board game known as called Quantum Enigma, which is your gateway to scientific discovery. So what's Quantum Enigma? It's a board game for 3 to 5 players. It's reasonably complex, so it's aimed at teenagers and adults. And it takes about 1 hour, 1.5 hours to play once you know how to play. The first play always takes a little bit more time. So the premise of the game, I'm going to read what the game, the box typically says on the back. Join a prestigious research group developing cutting-edge quantum technologies crucial to the outcome of an ongoing war. Each team member has a unique expertise and role to serve, from building experimental apparatus to developing quantum or classical algorithms. You can directly work on the projects, collaborate with other team members, and even steal their notes for your own benefit. The outcome of the war depends on your success. But beware, there is a spy among you who is trying to sabotage your work. With a variety of strategies to choose, random selection of the spy, and dynamics strongly dependent on the players' personalities, every game is different. So I hope it kind of summarizes the premise of the game. You're a bunch of, every player becomes a member of the scientific team, and you want to collaborate to create technologies that will help you win the war. It's the we've been working on this game for quite a while now, I just wanted to say, and it was inspired by events in Bletchley Park, where scientists, cryptographers, and technologists work together to break enigma code. And it is honestly, even though it is an excuse to have a collaborative strategy game, I wanted to say that taking into account the recent events, we don't want to convey in any sense that war is a fun thing. It's definitely a terrible thing to go through. This is an excuse for a collaborative type of game. So the aim of Quantum Enigma is to help you understand what quantum technologies are and provide guidance in searching for more information independently. We are going to launch a Kickstarter campaign soon. This summer, you will be able to find Quantum Enigma under the Games tab. So you are encouraged, please go check Kickstarter once in a while for the campaign if you're interested in this project. So the key feature of Quantum Enigma, here to the top right, you can see the elements of a Quantum Enigma. This is the prototype that we used to play test many times. First of all, games mechanics reflect structure of real scientific projects. One of the project's features in the game is conducted by Silvia Bergamini at the Open University. So what you can see is the board where you have a couple of elements. You have cards, action cards that allow you to interact with other players. You have character cards that tell you what your expertise field is and how you can contribute to the projects. And then you have those hexagonal cards, which are the project cards and expertise cards. And they are used to assemble experiments, as it is shown here, for instance, to the right or here. You acquire those cards and you build the big experiments. And once the experiment is finished, you can improve your capabilities and this way be more robust against attacks of the enemy. There are enemy cards that is simply just a challenge at the end of each round that you have to go through. And the better technologies you have, the easier to go through the challenge. So the game shows the applications of various quantum technologies and how the research group work pretty well, I think. And also it comes with scientific explanation of each element. So here I showed one of the pages that explains one of the cards. It was quite an effort to compile this document so that every person who is interested in science behind can, even during the game, just pick up the booklet and read about an interesting part of the research they are doing. Most importantly, the game is fun to play, and there is no need to even understand science. We designed it this way because we are aware that if you have a couple of people playing the game, some of them might be interested in science behind, some of them might just want to enjoy the game and don't want to read, a page-long description of an experiment. It's not what they're looking for. That means that everyone can find something enjoyable for them. And the game is complex enough to satisfy experienced board game players. We made effort to make sure that every game is different and you can play many times without feeling like it's repetitive. Well, with this accent about the game, I would like to say thank you. That's all what I wanted to present today. I want to say thank you to the Open University, Silvia and Andrew, who helped develop the game, and also sponsors of the research I presented today.
Thank you very much, Kasia. That was an absolutely fantastic talk. One downside of the online format is no round of applause. I tried it once, but the speaker couldn't hear it, so it's just me on my own listening to applause. But thank you so much. That was a really good drilling down to the basics at the beginning and then expanding on that to help explain the work that you're doing, which is obviously extremely complex, and you've explained it in a really good way. For everyone watching online, we're happy to receive questions for the speaker if there are any. So if you want to email stem-sps-iop-lecture@open.ac.uk, we need to come up with a snappier email address. The link should be there on the page that you're watching from. I also wanted to say that if anyone wanted to be kept up to date with when that Kickstarter goes live, I'm happy for you to just email that email address and say that you're interested in that, and I'll be sure to send an email out to people who are interested whenever it's live. Kasia will let me know. That's fine. So we can do that. I had a couple of questions while we were waiting for some to come in. First was a technical one. Back at the beginning, you showed a picture of your, I think it was a picture of your condensate. I think I understood it correctly.
Condensate.
With the laser and how it got smaller. Yeah, I wanted to just know what the size that was, your final size.
Oh, our final size of this cloud, it's a couple of micrometers across. Yeah, so, okay, so this camera that you're looking here we are talking about probably like 300, 400 microns total length. Yeah, probably about 250, 300 microns total length. And then as you go to the very right, it's pretty small. So here it's going to be, so this picture in particular is going to be about 7 by 10 microns length. But also to be fair, this picture is taken after we already dropped the cloud and allowed it to expand a little bit, because the trap, I mean, normally if you just keep it in the trap, it would be so deep that across it would be just like a pixel or two. You wouldn't see it very well.
That's what I was just thinking. That's about the same size as a pixel on
Yes.
the camera, just to give people an idea. Let me just check if we've got anything coming in. Normally it just takes a little while for us to start receiving them. I also wanted to ask, in terms of my research area, which is obviously space instrumentation, I know that there are developments towards a quantum gravitometer, so measuring accurately gravity from orbit in order to detect changes in density and therefore minerals and things on the surface. I don't know if you know anything about that. I wanted to ask if it's a similar kind of technique where they're using a BEC interferometer for that, or if maybe you don't know.
I mean, okay, so it's probably going to be similar. As far as I know, so for instance, okay, let's go back. So for instance, this one here, right? This is a gravimeter. This one is big and bulky. So yes, you can use atoms for gravimetry, meaning that you could also use them probably in BEC state. At the moment, the main reason why people try to use BEC is because they want to confine them in a small package and make this kind of area the biggest. It seems that for gravimeters, there are some demonstrations, I don't really remember very well, that show that you can somehow kind of suspend atoms in free fall, and they don't really fall that far, and just keep them for like 30 seconds in the same place and still get very good sensitivity. So it's very similar topic, I would say.
Okay, fantastic. We've got an email from Andrew. He asks, how can the large-scale lab experiment be miniaturized to work as a position sensor that can be flown on an aircraft? Yes, in terms of, a black box instrument that you can have in the cockpit.
Well, okay, so first of all, the guided interferometer is the reason why we are you're trying to reduce the sizes while we are doing guided interferometer, because this case of experiment, as I'm showing here, as I said, is going to be very big, because if you have ballistically moving atoms and you kind of split them, they move just the long distances over a certain amount of time. So we are doing this guided one because then it's kind of slower. You can move them around in the bigger loops and get better sensitivity. So at least in an idea that you don't need physically big size. This is the first important thing. Then obviously the question is, how do we miniaturize all of the laser equipment responsible for it, all of the coils? There is a lot going into it. because yeah, this is currently the way the experiment looks like. So there has been already a tremendous progress in miniaturizing laser sources. Also, you can try to make this experiment kind of more efficient so that you don't have to use that powerful laser beams. That's very helpful if you don't need that much power. Some parts of the application will need more power than the others, but you can try to minimize that. The same with the coils, because we need a bunch of coils to like offset the stray magnetic fields and create magneto-optical traps and so on. So this can be also miniaturized. There is lots of effort to create like magneto-optical traps and dipole traps and all of those optical elements on chips. This is another thing. So you try to fabricate a very small scale device on a chip. And there is a progress on like making light fibers that allow light to propagate through the chip. And then there is kind of like a grating that launches the beams into space, and they kind of cross in one space. And this is where you can create the trapping region for the atoms. It's not something we use in our lab, because in our lab, you need to change experiment often enough. It kind of grows organically. But once you have a design, you can try to incorporate all of those miniaturization techniques to make it more of a physical small package. I don't think it's going to be a shoebox yet. Maybe like half of a wardrobe or something, but it's already like a dresser. Yeah, it's probably a dresser side right now. But we are getting it. It's the direction of getting it shoebox.
Okay, interesting. Thank you. The questions are coming in thick and fast now. So Siobhan is asking, how do you control the mirror that moves the dipole trap around, and can you move it while you're running the experiment?
Oh, okay. So
this is about the yeah.
Yes. So here we have atoms in the dipole trap, and we are moving it back and forth. So this is actually not a mirror. This is acoustic modulator. So what we have is just the beam coming in, and then there is a crystal inside, which is modulated with RF frequency. And this RF frequency creates a diffraction. So the beam basically kind of deflects at the angle. So if you change the frequency of the wave that goes through this crystal, you can very quickly change the deflection angle. So this is the way we are doing right now. We are considering using another technique, because this one has some drawbacks, obviously. It can be very fast, basically, tens of nanoseconds, and you already switch. There are new techniques with mirrors, position mirrors, which are like composed of many small elements, and you can very quickly adjust their position with piezos. So we are considering using something like this, because this way, nowadays they are fast enough to do what we want, and the profile of the beam is going to be better. In this case, yes, we are doing it, we are deflecting it during the experiment. So as the atoms are moving around, we are moving also the beam so that they kind of enclose this area.
So that the mirror, is that almost the same as they use in astronomy for atmospheric corrections?
Oh, this new type of mirror?
Yeah. I can't remember the name of it.
I don't know that they are using in astronomy, honestly. I wouldn't be surprised if it came from there. I mean, we're happy to deal with devices that we already had in hand, but this mirror I'm talking about, it's, probably less than an inch big, and it can, correct the surface.
Mm-hmm. It sounds very similar. They use the same in because the atmosphere blurs the light from the stars, and they can correct very quickly for the atmosphere. Okay, we've got more questions coming in. So Alex has asked a few. How does the accuracy of modern rotation sensors compare with gyroscopes, and how does the potential accuracy of a quantum sensor compare to that?
Oh, okay. I don't have the graph, unfortunately, with me, and so there are quite a few different rotation sensors, right? So there are gyroscopes, there are MEMS, which I don't really remember how precisely they work. They are mechanical, though. So if you look at the graph, you're going to have, it's like an order of magnitude more sensitive every next solution is. So you have mechanical, then you have MEMS, then you have the atom interferometers, and then the atom they have light interferometers, and then you have atom interferometers, which will be potentially next order of magnitude. So to give you an idea how unstable rotation sensors are, it's like if you start measuring rotation, the question is how long it takes for the rotation sensor to drift away, because this is the main problem in this case. Our standard, like, I don't know, rotation sensors we have in phones or in other, it's a matter of minutes and it's already drifted away. It's like you cannot measure accurately enough. Then you have MEMS, then you have the light interferometers, like Honeywell, for instance, has a very high, accuracy. This one you can keep measuring for half an hour and you still have good enough accuracy. So you can see the problem is that measuring for hours and still have not drifted away is a challenge in our case, in case of gyroscopes. So I am talking, a standard mechanical, it's minutes, it's less than minutes basically, and it's already gone.
Okay. Further question from Alex. So he's asking, you mentioned that sensor motion is a problem for the beams of atoms. Why isn't that a problem for beams of light? Or is it?
Oh, I mean, no, for the beams of light, it's because they don't have mass, right? So they're not going to kind of smash against. Like if you have light as even in, like, let's say this configuration, all was going to see if you start rotating it or like moving is just that one of the arms just get relatively shorter than the other to each other. So another thing is also, light is also mostly guided in optical fibers. It's very well defined where the light is.
And how fast are your atoms moving compared to speed of light? Like, is it fast or is it not really?
Oh, no, it's very slow. So our atoms move, when we split them, the velocity is like 12 millimeters per second.
Okay. Okay, that's slow.
But the only reason why we get any kind of gain is because they are so much heavier. So they carry more energy with them.
Okay. I'm going to finish off with a couple of maybe a bit broader questions that you might have an answer for, you might not. Let's put you to the test. So first of all, I guess, how close is your rotational interferometer to, say, a commercial product that could be used?
Oh, okay. So the person asking maybe is familiar. There is something known as technology readiness level. I think it's scaled from 1 to 10. And it goes like this: from 1 to 3 is proof of principle. 3, 4, something like that is going to, it's still a proof of principle. And then from 4 to 6 is bringing it to the commercial stage. And then basically 6 up is just the companies refining the product. I think we are somewhere around, what we do is probably somewhere around 4, 5. So the proof of principle has already been there for quite a while. As I said, for the 3 years, we've been just looking for the noise sources, intrinsic limitations of this kind of interferometer, and so on, which is a tedious job. It's also lots of kind of groundwork, which is required to be done. There's also physics and fundamental phenomena to be still understood. But it's not just a proof of principle anymore, like in a sense, hey, look, we have a fringe, because this is not enough. But I mean, after us, someone will have to take it and combine with this miniaturization techniques I talked about. So yeah, we are doing it for a sponsor who has a way or an idea how to take this kind of developments we have and combine with more commercial approach.
Fantastic. This one might be even harder. So in terms of the quantum sensing and all the kind of technology you've talked about today, can you foresee any kind of applications that will make a difference to the ordinary person going about their ordinary lives? Like, how are they going to see this technology come to fruition?
Well, it's a difficult question because, since we don't have it fully developed yet, right? It's always the application comes with the fact that we already have something and people can come up with, we could do that and that. It was the same with computers. I think initially computers people were thinking it will be just mostly for breaking the encryptions, but in reality we use it on a daily basis for pretty much everything that we do.
I think the quote was, one day we might see a computer below 1.5 tons.
Yes, one day. So I expect that with those technologies will be similar. They are going to evolve in an organic way. But we already know that some applications we might think of are optimization applications. So the first stage of quantum computing will be probably cloud-based quantum computing, where you have the big machines that have certain computational power, maybe some limitations, and people can apply for time to solve some problems on them. So I'm guessing there are going to be mostly optimization problems, like, logistics companies trying to save on fuel or something like that. This is like what comes to my head. Rotation sensors, for sure. This is what we are working right now. This one is probably a matter of couple of years, and it will be more and more available to like, maybe not an ordinary person, but maybe submarines. Or I was talking to someone recently about self-driving cars, and apparently one of the problems with self-driving cars is that you need a couple of ways to navigate. So you need a camera, you need a distance measurement, you need GPS, but you also need inertial navigation because GPS has a limit, and you really want to know where your car is precisely at the moment. So the inertial sensing could actually go there. Maybe not necessarily with atoms right now because it's going to be quite big, but again, I don't know, it's future. And yeah, like any kind of medical devices that measure magnetic fields or diagnostics of brain and so on. That's something where we could find increased sensitivity useful. And by the way, everyone is using GPS that uses atomic clocks, and atomic clocks are an example of quantum devices which are already in use.
Fantastic. I think there's one last question which I want to ask. Maybe it's a bit of a joke question, but when can we expect a quantum enigma type game for toddlers? I need to start mine early.
Toddlers. I was thinking about younger kids. Okay, so the actual idea is, I think we are working to start a campaign on Kickstarter, and Kickstarter always has stretch goals. Like, if we hit this many and this many supporters, we can do this and this. And I was actually considering that one of the the stretch goals should be kind of revised set of rules to use similar elements from the game for younger kids. Like that you, for instance, assemble the experiments. You don't really have to go through the complexity of the entire game, but perhaps you could like assemble smaller experiments, and who does it first wins or something like that. So I was actually considering going this direction at some point. Maybe not toddlers. There is a book, Quantum Mechanics for Toddlers, though, I think.
Fantastic. Thank you so much. So I think that's it for questions. So if everyone would like to give Kasia another round of applause in your living room, bedroom, wherever you happen to be. I'm just going to finish off by reminding you about the next talk that we're advertising, which is the OU. It's an OU inaugural professorial lecture, and that's at the same time as our normal slot. So that's the 10th of May, which is the second Tuesday in May. And we have Professor Leslie Budd, who will be giving a talk entitled From Urbanite to Astronaut, the Territorial Economics of Space. If you Google Leslie Budd, and inaugural lecture. The first couple of links will be the link to his talk and give you the details of how to sign up for that. You can either attend in person in the Beryl Lecture Theatre in Milton Keynes, or there's going to be an online stream as well. So I just take this opportunity. Thank you so much, Kasia, for taking your time to talk with us today. It was a fantastic, interesting lecture, and I think you really boiled down the subject in a way that everyone could understand, and also talked about the cutting edge stuff that you're doing. So that was really fantastic. Thank you so much. And for everyone who's out there, I hope to see you again soon. Next time we host a lecture. Thank you so much.
Thank you.
Bye-bye.